Okay, Algebra 2A, welcome back. This is a video for lesson 33. And this is an introduction to our statistics. Kind of the first time, actually second time we've been talking about statistics. We've done mean, median, mode, standard deviation, range, and then today we're going to start introducing statistics, and it's kind of an introduction into probability. Our goal today is to apply different counting principles. So we're going to look at ways that we can count outcomes, which is sometimes can be very large numbers. Like if you think about the number of outcomes there are for the lottery, there's 292 million different outcomes that you could get from those numbers. So we're going to kind of look at how do you count that many outcomes without wasting a bunch of time. So that's our goal today, is to use different types of counting methods. We're looking at probability experiments. An experiment is any process that results in one or more outcomes. Outcomes are the possible result from a probability experiment, and then the trial is the process repeated one or more times. So our first counting principle that we are going to use is the multiplication counting principle. So here we have a restaurant offers a single dip of ice cream and a single topping for dessert. The ice cream choices are chocolate, vanilla, and toffee. The topping choices are chocolate, caramel, and strawberry. How many different desserts can be ordered? So to do this, we can make what's called a tree diagram, and then we'll also look at how the counting principle fits into this. So our first choice, we have three different ice creams: chocolate, vanilla, or toffee. Now on the chocolate, I could put a chocolate topping. I could put a caramel topping, or I could put a strawberry topping. So I have three different ways to just top my chocolate ice cream. On the vanilla, same thing. I've got 1, 2, 3 different ways to make a vanilla, and then I've got 1, 2, 3 different ways to make my toffee. So if I count that up, I've got 3 for each type of ice cream, 3 toppings. That's going to be a total of 9 different desserts. Now another way we can come to that count is taking the number of ice cream choices times the number of topping choices, and that's going to equal our total, which is 9. So that is our what's called the fundamental counting principle. We can take the number of outcomes in the first choice times the number of outcomes in the second choice, and that's going to give us our total number of outcomes. New concepts, a sample space. A sample space is your set of all possible outcomes. So our sample space from above would have been 9. There are 9 different outcomes that were possible. In the lottery, there's 292 million different outcomes. So the sample space is what we're using these counting principles to find. How many possibilities are there? And then we can start finding probabilities from there, which we'll do later on in the year. An event is the outcome or set of outcomes. So in the lottery, the event could be the winner. So the winner would just be one of those outcomes. So 1 out of the 292 million. An outcome could be a certain type of ice cream from above. So the outcome is usually in probability, the outcome is what you are looking to find, and then you're going to find its percent chance of happening. But the outcome is what you are looking for. The adding counting principle looks at different choices and how you add your choices together. So it says, suppose a trial can result of any n outcomes from one category and n sub 2 outcomes from another category, and so on. If there are k different categories of outcomes, then the total number of outcomes can be n sub 1 plus n sub 2 plus all the way to however many choices you're looking at. We will talk more about mutually exclusive as we look at probability, but mutually exclusive is when 2 events have no outcomes in common. So we'll talk more about that as we get into probability. But here we look at example 2, find the number of outcomes in each event. In a local restaurant, you have a choice of 3 beef dishes, 4 chicken dishes, or 2 vegetarian dishes. So here, how many total outcomes do I have to choose for dinner? Well, my first choice, which is 3 beef dishes, my second choice, which is 4 chicken dishes, and my third choice, which is 2 vegetarian dishes, I would have a total of 9 dinner choices. So you can kind of think when you're going out to eat, you could have this, you could have beef or chicken or vegetarian. Anytime you hear that word or, that's gonna start to trigger that we need to use the addition counting principle. So the addition counting principle will give us 9 total outcomes. Now in part B, it says choose a prime number or a multiple of 4 or a multiple of 9 by choosing a random number from the whole numbers 1 through 20. So choosing a prime number or multiple of 4 or multiple of 9, since we have that word or, that's going to trigger that we're using the addition counting principle. So 1 through 20, I'm going to count up multiples of 4. That's 4, 8, 12, 16, 20. So there's 5 total that are multiples of 4. So I'm going to keep track of that. I'm going to save the primes here. Multiples of 9 are 9 and 18. So there's 2 multiples of 9. And then the primes. We'll count those up. So prime numbers are numbers that are only divisible by 1 and itself, and 1 is not a prime number, so we start with 2. So 2, 3, 5, 7, 11, 13, 17, 19. So when I counted all those up, I got 8 total. So there's 8 total prime numbers. Now here's where the mutually exclusive is. So there's 3 events here that I could choose. I could choose a prime, a multiple of 4, or a multiple of 9. I'm looking at adding those 3 categories together, but I do need to check, are there any outcomes that occur in more than one event? Well, in this case, no, because primes, they're not divisible by anything except 1 in themselves. So a multiple of 4, multiple of 9 would never be prime. Then I look at multiples of 4, multiples of 9. There are no common multiples of 4 and 9 in the set 1 through 20. Eventually, we'd get some when you get to 36 and some bigger numbers, but there are no numbers that are both divisible by 4 and 9. So this is mutually exclusive. Each event has its own outcomes. They have no outcomes in common. So I'm going to add all of them up, and I would get 15. So sometimes we will get where they're not mutually exclusive, and that would mean that we'd have to subtract out any of the outcomes, that happen in multiple events, because we don't want to count those twice. So there I'd use the addition counting principle. Again, the key word you're looking for is or. Anytime we see or, triggers that we're using that addition counting principle. Next, we're going to continue talking about the fundamental counting principle. So the fundamental counting principle was a method we could use for the very first example with the ice cream. So suppose k items are to be chosen. If there's n ways to choose the first item and n ways to choose the second item, and so on, there's n times 1, n1 times n2 times nk ways to choose all k items. So here you're looking for using multiplication to find the total amount of outcomes. So in problem 3, we're looking at a student is choosing a 4-letter password for an email. So we're using letters. So we're going to think about the total number of letters in the alphabet. And then here we're going to have 4 letters. So you could have a letter and another letter and another letter. The keyword and, whenever we have and, that's going to lead us to using the multiplication counting principle, which is also called the fundamental counting principle. So how many passwords are possible if letters can be repeated? So if we have 4 letters possible in our password, the first letter could be one of 26 different options. Then our second letter, since it can be repeated, we'd have another 26 options for our second letter. Times our third letter, we'd have another 26 different options. And then times our fourth letter, we'd have another 26 different options. So to find the total number of passwords, we're going to multiply 26 4 times. And we'd get 456,976. So a password with 4 letters will only give you that many different outcomes. I know it seems like a lot, but that's something that a computer program could guess a password pretty quickly, get through all 400,000 of those different passwords. So how many passwords are possible if letters are not repeated? So if letters are not repeated, I'd have 26 letters to choose from still for my first letter in my password. But then after I've used the letter, now my second letter, I only get 25 options because I've used a letter. And then I've used 2 letters. Now I only get 24 options. And then lastly, I'd only get 23 options. So to find my total number of passwords if letters cannot be repeated, I'm going to take 26 times 25 all the way down to 23. And I would get 358,800. So we have less passwords because now we've thrown out all the passwords that would have duplicate letters. So we're going to have even less options. Most security requirements for emails and things require 8 letters, because once you get up to 8 letters, you start to see a lot more passwords, and it's a little bit harder to hack into. So most require 8, and then you throw in symbols and numbers and everything, and you start to get a possibility of a lot, millions and billions and billions of different passwords. To finish up, we'll look at what independent and dependent means as far as probability. So first, independent. Independent is 2 probabilities events where the second event is not affected by the first event. So a classic example of an independent event would be rolling dice. So every time you roll dice, you have a 1 out of 6 chance of getting a certain number. So even if you'd roll like 6 5s in a row, that doesn't mean that your probability on the next roll is going to be any less for a 5. You're always going to have the same probability every time you do the event. Dependent, so dependent event is where 2 probability events where the second event is affected by the first. So let's say you have a jar of candy, you have Snicker bars and you have Butterfinger bars in your jar of candy. As you pick out, so maybe you pick out a Snicker bar. As you pick out a Snicker bar and you take it out and you eat it, you've now lowered the number of total candy bars in your jar, and then you've also lowered the number of Snicker bars in your jar, which is going to change the probability for the next time you go and pick out a piece of candy. So when your probability event that you do starts to affect the probability after, that is going to be called a dependent event. So dependent is where your second probability is dependent on whatever happens in your first probability. So we're going to look at a couple of scenarios and then decide if we have independent or dependent. So example 4 says a collection of coins contains a penny, a dime, a nickel, and a quarter, and a dollar. Determine whether the events in each case are independent or dependent. So we choose a penny and then choose a nickel if the penny is not replaced before the nickel is chosen. So we're going to choose the nickel, choose a penny, then choose a nickel, and then the penny is not replaced. So you pull that penny out of your jar, your bag, you've now lowered the amount of coins in them. And if you don't replace it, now there's less coins in that bag, which is now changing the probability for the next time when you draw the nickel. So since the penny is not replaced, you've now changed the total number of coins in the bag for the next time, which means that you've now changed the probability. So that would be a dependent situation. Another way you can think of it is dependent, your sample space is going to change. So your total number in there is going to change here. Your sample space in independent, your sample space is unchanged. Part B, you choose a penny then a nickel if the penny is replaced before the nickel is chosen. So if you pull that penny out and then you put it back in, you've now replenished the total number of coins that are in that bag, which means that the next time you do the probability, you're going to have the same amount as you did the first time. So your sample space is unchanged, and then that means that your probabilities are unchanged as well, so you have an independent situation. We'll continue to discuss dependent, independent, because it's going to start to develop what type of formulas we use moving forward with probability. Lastly, there are 8 students working on a school newspaper. The 8 students will be lined up in a row for a picture. How many different ways can the students be arranged? So here we'll draw out all the spots possible for these students to sit in their picture. We got 1, 2, 3, 4, 5, 6, 7, 8. So if we look at the far left position, there's 8 possibilities for somebody to sit there. Then we're going to use our fundamental counting principle. Since someone is sitting here, there now leaves only 7 people for that next position, then only 6 people for that next position, and then only 5 people for that next position, all the way down to 1. And then we're going to multiply everything together. So that's going to be 8 times 7 all the way down to 1, which would give us 40,320 ways that the students could line themselves up. That pattern is also called a factorial, which is used with an exclamation point. So that is another topic that we'll continue to investigate. So factorials are used a lot in probability and statistics calculations. So it's a pattern that shows up a lot, and we'll continue to talk about that. But there you have it, some quick ways to count outcomes. We had the addition counting principle, and then also the fundamental counting principle, which uses multiplication. Thanks for joining, and we'll see you next time.